We're interested in smart materials, which are materials which have the ability to change their shape or change their colour or change in other ways, change their physical properties in response to external stimuli. Now the materials which we're interested in particular are materials that change their shape, so they function a bit like artificial muscles, hence we refer to them as artificial muscle materials, and they have the ability to move or change shape in response to external stimuli such as the application of an electric current or a change in temperature, or when they're placed within a strong magnetic or electrical field. We use shape memory alloys, and in this particular project we were trying to build a robotic tentacle, and we've used shape memory alloys which are configured to contract when you pass a small electric current through them. In fact, the electric current heats the shape memory alloy up and causes it to contract due to a change in its crystal structure as it's heated. So we built this robotic tentacle out of a soft material which is fabricated by 3D printing, so you can see the material is soft and bendy, and we incorporated into the structure passageways into which we could introduce the smart materials which allow it to move. So by passing an electric current through the muscle, it contracts, which can create this lifelike movement. You see it moves in all different directions. It can move through 360 degrees. So it's capable of this very lifelike movement, and it's made out of soft materials. So the idea is that for example, it could work safely within close proximity to a person, whereas robots made out of hard materials can sometimes be dangerous. We're exploring the idea of making robots which are safer because they're made out of soft materials. Well, the tentacle design, which I've demonstrated here, could be used in a number of different ways. For example, we imagine fitting a small camera, a video camera, onto the end of the tentacle. So you could create a camera which would look in lots of different directions to explore an environment. For example, you could use it to look inside a place like a car engine or something which was difficult to reach, or difficult to see inside. You could make a camera which could look inside a hard-to-reach place. Or, for example, we could put a tactile sensor on the end of the tentacle so it could explore in a tactile way its environment. Or perhaps you could have three of them which together would function as a robotic gripper. The structure of the tentacle is made by 3D printing, but it's not printed in a rigid material, it's printed in a soft rubber-like material. And 3D printing means that we can quite easily make very complex shapes without having to worry about the conventional limitations of, for example, moulding or machining. With 3D printing you can make almost any imaginable shape. So we've been able to form these soft structures as a single piece, including all the internal cavities which are needed into which the artificial muscles are fitted. So quite easily we can make a very complex structure. Also, as we're aware, 3D printing is increasingly affordable, so it's possible to make quite a complex robotic device relatively cheaply and easily, whereas in the past it may have cost thousands of materials to make a robot such as this tentacle. Now we can make it for hundreds of pounds.
Okay, so what we've got here is an electroactive polymer, which is a membrane around the outside. And that's clear, a nice transparent elastic membrane, and it's been stretched over this frame. So this is the very simplest form of artificial muscle that we're going to demonstrate. And in the middle you see a black electrode material. So we have electrodes on both sides. And you see the wires coming down on the right and the left here, which are, we're going to apply some electricity to those. And the ball in the middle is going to move up and down. And the reason it moves up and down is because we have these electrodes on the top and on the bottom of the material. When we apply electricity, these electrodes expand. When they expand, the material becomes slack, it becomes loose, and the ball then is free under gravity to move up and down. So what this experiment does is to show us two things. First of all, it shows that the membrane can deform, can show response under electrical stimulation, but it also shows that we can turn the aerial expansion of this membrane into something really useful, which is moving a ball up and down. So of course, in this case, the ball is just showing movement, but we could have it pressing a switch, we could have it configured as a pump, all sorts of other things. So all I'm going to do now is just switch on the power supply to it. You'll see that it moves up and down. And I hope you can see here, I'm not going to put my hands too close because this is running at a reasonably high voltage. What's happening is the ball is going up and down because the membrane is expanding. Now later we'll take the ball off and you should be able to see the membrane expanding on its own without the ball. Okay, they're reasonably robust materials and it should be able to do this for quite a long time, provided we don't increase the voltage too much. If we were to do that, then the material is going to degrade. And that means, of course, that there are some really interesting avenues for research in this area to increase their robustness, to increase the number of cycles that they can run on, and to make more effective machines, the kind of machines that you can make and then send out into the environment without them breaking. Here we have our actuator that we saw before, where we've reconfigured it so that it is working as a kind of chromatophore. And a chromatophore is a cell that's used by many organisms to change their colour. So for example, squid and cuttlefish and octopuses will use their chromatophores to change from a white structure, from a white coloration, maybe into a brown or to a more coloured appearance, and also for communication and to attract mates and to do all sorts of really interesting communication. Of course, they need that for camouflage, to hide themselves in their environment too. So one application for these technologies is for artificial camouflage. Of course, we don't just need to have camouflage which hides people or hides things. We could also maybe turn these materials into some kind of wearable skin, for example. And in that case, we could use these artificial chromatophores as a kind of display. You could imagine having yourself covered in some kind of second skin where these chromatophores will be changing color over your body, over your clothes, and they would add a new dimension to communication and also maybe to fashion. So in this simple example here, we've got the membrane. I'm not going to touch again because this is high voltage stuff. So we've got our simple membrane, in this case, with high voltage being applied through these compliant electrodes. And so the black material here is acting in two purposes. The first is it's conducting the electricity into the center and conducting the electricity away afterwards as well. And also, because we're using this here as a chromatophore, it's the color change that we want to capture. So you can see here that the spot, which is beating quite fast, about 4 times a second or so, or 2 times a second I think in this case. What's happening is the spot is expanding and the dark area is getting bigger. So if we were to step away and we'd have lots of these across some artificial skin, then the coloration of the organism, or in our case, our clothing or second skin, would change. Now here we've got this as a black material, but there's no reason why we can't have other colors too. And of course we can start combining them. So you can imagine that we could make some smart skin which is not just black, not just changing color from white to black, but also maybe changing color using the red, the green and the blue, and we put them all together, we can have a nice color changing artificial skin. Of course, this isn't the only application, and these membranes here can be used for all sorts of things. So from pumps to artificial muscles, even we can use these to create complete organisms. So for example, if you were to take this kind of structure and we reconfigure it a little bit, it would be a little bit like the pumping of the stomach, the peristaltic pumping of the stomach. Well, that means that we can use these organisms, these artificial organisms, instead of conventional robotics. So instead of using motors and gears and other things which we would traditionally use, we'll use these instead. That also means that we are not faced with the problems that we have with conventional technologies. For example, if you're going to make a motor, it's got magnets, it's got windings, it's really quite a complicated structure. And that makes it more difficult to make these motors, these things, smaller. With these materials, on the other hand, we can make them quite small. We can even go down to a few hundreds or even smaller of a few hundred micrometers. This is really very small things, almost as thin as a human hair. Now, if we can do that, the facilities for these things are really quite novel. Not only that, because these materials are soft, they're very attractive for interactions with other soft things like the human body. And the human body is soft, and we like to interact with other objects which are soft too. So you can imagine taking these materials and creating devices that go on the outside of the body and interact with them, but also go inside the body. So now we're moving into the ability to create implantable medical devices which are soft. That's really attractive. Not only that, but the mechanisms that we use for fabricating these can be personalized. So we can end up making a structure which is geared to a particular person. We can take a scan of a person, an MRI scan for example, and then we can fabricate some soft structure using these technologies, and then we can implant that into a person and treat an illness. Now of course we're a few years away from that, and there's lots of research that's got to go into this. So if I list off some of the things we've got to look at, we've got to look at these new materials. We've got to make them more effective, more efficient, make their lifetimes longer. We've also got to reduce the voltage, the operating voltage of these things. If you're going to implant a medical device, you can't have it running at the high voltages that we've got here, the kind of thing that you can't touch. It's got to be at a safe voltage. So there's lots of interesting research. Not only that, we've got to make these things biocompatible. Either biocompatible in the sense that we're going to put our robots out into the environment, and they're going to have to be compatible with the environment, but also if you want to put it inside the human body, it has to be safe as well. Okay, so in our laboratory we're interested in all types of soft robotics, and to do that we look at these new materials, some of which work at high voltages and they're really quite strong. Some of them, like the ones we've got here, work at much lower voltages and they're not quite so strong, but they really do move quite a lot. Now because they're working at lower voltages, that's quite attractive for some immediate applications, where the high voltage applications, high voltage actuators and materials, we've got to work on those quite a long time before we can start using those in medical applications and so on. But these low voltage actuators, the ones I'm going to show you now, they're really quite suitable for use immediately. So this one is working at a voltage of about 2 or 3 volts, the kind of voltage that will now enable us to put these materials into the human body. So what I'm going to do is I'm going to show you this material, which is a polymer, but it's covered on both sides with a gold electrode. And the gold electrode is soft enough and it's been configured so that when the material bends, the gold doesn't break, so it maintains conduction. So what happens when I apply electricity to this? So when I put my voltage across these membranes, they bend. Well, some of the materials we've got will expand, and then we can look at them as artificial chromatophores, colour changing devices and so on. But these ones are really quite special because they bend and flex. And then we look at them and think, oh actually that's quite interesting, we can use them for applications, for example for swimming. So here we can make swimming robots and we could do all sorts of interesting things. Here in this case we have a robot which looks a little bit like an anemone or a jellyfish or something like that. And what's happening is that there's a beating action where the water is being pumped from one side to the other. Okay, so this is a type of smart material that we call an ionic polymer composite material. So it's got gold on the outside and it's got a wet polymer on the inside. And then all we need to do is take our box, which is applying 2 volts or 3 volts or so, and you can see that it bends and twists. Now it's moving an awful lot, and that involves some interesting motion of the ions inside the material. But you also see when I hold down the voltage, it moves one way and it comes back again. So there are really interesting properties here which we need to assess and we need to work with. Of course we can take this material and we can configure it into some really interesting structures. And if I hold up one here, I've got an example which is like a snake structure. And so you can see there's 1, 2, 3, 4, 5 segments. And if we apply electricity to each one of those segments in a different way or in a different order, we can get this structure to swim backwards and forwards like this. So this here becomes the body of a robotic organism or a snake robot. With no motors, with nothing else in there, just with that. And of course all we need to do then is to put a controller or a head onto the robot, put a power supply on, and then we can get this thing to swim. So they're very attractive, very interesting structures. Not only that, we can make these things really quite small. They can be miniaturized down to the micro and even to the nanometer level. So they're very attractive materials. Again, if we're going to use these materials, we still have a fair amount of work to do in perfecting the chemistry, so we need to work with the chemists, looking at the mechanics of the structure, and also working out what's the best way to use them, which is really quite an interesting challenge. So where before we saw the cuspid actuator, the star actuator, which was really quite large, here I've got an example which is much, much smaller. I hope you can see that one. So that's only about 1 centimetre across, and when I put electricity on this one, those little star shapes in the middle will open and close, open and close. So we've got a valve here, and an active valve, which looks a little bit like the valves inside the heart. Inside the heart, there's a cuspid valve, which is made from 3 parts that opens like a leaf, like so. But in this case, we can apply electricity and we can have an active valve, something which is beyond nature. And we'll have to see whether we can use this for lots of interesting applications, possibly for pumping fluid, for moving things around, or even to control the flow of fluid.